Hello, awesome Algebra 1 students, and welcome back. In this video, we're actually going to go through all of the properties of exponents, all 5 of them. Now, if you've been following along, you only know about 3. There are actually 2 additional properties of exponents that we haven't talked about yet. So we're going to go through all 5 properties, do a couple examples, and we're going to look at how the properties work the long way and how the properties work the short way. So grab a piece of paper and a pencil, and what you're going to want to do is you're going to want to set up your piece of paper like this. So on your piece of paper, you're going to want to leave some space at the top, and then you're going to divide it into 2 sections. We're going to look at the long way of how the property works and the short way for how the property works. You see my Boba Fett outfit today. Okay, so we're going to go through all 5, yes, you heard me correctly, 5 properties. Let's go ahead and start with our first property, which is called our product of powers. Now remember, when you're looking at the name of the property, it's actually classifying it as well. We are looking at expressions that are products, and the factors in these products are powers. So we're going to look at product of powers. We're going to go through an example the long way, and we're going to go through an example a short way. So get your papers set up, and here we go. So here's our example the long way. Let's say that I have x to the 4th times y cubed times x to the 5th times y squared, okay? So I basically have a product with 4 factors, and each factor is a power. That's why we call this a product of powers. Now, in a product of powers, you can always, the long way requires you to expand everything. So that means I'm going to expand each power into its individual factors. So x to the 4th power is x times x times x times x. And then y to the 3rd power would be times y times y times y. And then x to the 5th power would be times x times x times x times x times x, 1, 2, 3, 4, 5. And then times y to the 2nd power would be times y times y. So in the long way, you would have to expand it and actually make it messier before you can simplify it and write it all out as a single power. Now, we can only write single powers out of powers that have the same base. So in other words, go in there and total up all the x's and total up all the y's. So I've got 4 x's here and 5 x's there. So really, I'm multiplying x by itself 1, 2, 3, 4, 5, 6, 7, 8, 9 total times. So I can write that as a single power. X times itself 9 times is x to the 9th, right? And then if you look at the y's, I'm multiplying y by itself 3 times here and 2 times there. So that's a total of 1, 2, 3, 4, 5. So that's y to the 5th. And I can't say that x times y equals y or x times y equals x. So I'm basically done here. Like I've done all the simplifying that I can do. I've applied my product of powers, but it required me to write out all of the factors. Now it was fine because my exponents were 4, 3, 5, and 2. But can you imagine if your exponent was like 24, 33, 55, and 276? Like, do you really want to write out that many factors? Probably not, which is why we have these properties and we have these shorter ways. So we're going to look at the same example now. I'll put it in a slightly different color so that we can differentiate it. So we have the same example, x to the 4th times y to the 3rd times x to the 5th times y squared. Our product of powers, the property states, what are you actually doing to the exponents of powers that have the same base? Like, how did I get 9 out of 4 and 5? How did I get 5 out of 3 and 2? I added them, because all you're doing is you're adding up the total number of factors. There are 4 x's here and 5 x's here, 3 y's here, 2 y's there. So keeping it all really the same idea, I'm just going to total it up. So I have 4 x's there and 5 x's there. So that means I'm basically multiplying x to the 4th and then 5 more times. I'm just going to add up those exponents. And then I'm multiplying 3y's here with 2y's here. So I'm taking those 3y's and I'm adding on the 2 more. That's why product of powers property says you add the exponents. Well, the 4 and the 5 gives me a grand total of 9, and the 3 and the 2 gives me a grand total of 5, and you get the same exact answer in a fraction of the time with a fraction of the work. So product of powers, when you have the same base, you can add the exponents. You have your long way and your short way. All right, set up the next example. Now we're gonna go look at our quotient of powers. Okay, up next, quotient of powers. So again, the property is telling us what we're looking at. We're looking at a quotient, and in the numerator and denominator, you're going to be seeing powers. So let's take a look here. Let's say I have x to the third times y squared in the numerator, and x to the fifth. Let's make that actually, instead of a y squared, let's make that y to the 8th. Oh, that's going to be too big because I'm going to have to write all this out. Y to the 6th times y squared in the denominator. Yeah, that works out. I like that. Okay, so x to the 5th times y squared in the denominator, x to the 3rd times y to the 6th in the numerator. Pen isn't working too well. I'm going to get rid of it. Okay, long way. So the long way, again, you have to write out all the factors. So in the numerator here, we've got 3 x's, x times x times x. And we got 6 y's. So times y, 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 y. I'm out of room. Oh, okay. Thank goodness we have a shortcut, right? In the denominator, we have 5 x's, 1, 2, 3, 4, 5, and 2 y's, 1, 2. Okay, so the long way always requires you to write out all of the factors. So you're taking all these products and you're expanding them. Now, what are we looking for? Well, we're looking for math that we can do. That's what simplifying means, do math. So in this case, I see some big ones. I know x divided by x is 1. So anywhere I see common numerator and denominators, I know that those are going to simplify to 1. X divided by x is 1, x divided by x is 1. But that still leaves me with 2 x's in the denominator, and because I can't create a big 1 out of anything else. So I was able to essentially, for lack of a better word, cancel 3 of the x's from the numerator and denominator. I see the same thing with the y's. I see a couple big ones as well. I see a big one here and a big one there. So I was able to cancel 2 of the y's, but it still leaves me with 4 in the numerator. So if you look, my final or my next step here is if I just kind of clean it up and see what I have left, I have y times y times y times y in the numerator and x times x in the denominator, because the rest of these were all canceled out as big ones. And then if we write those both as single powers, that's y to the 4th, because there's 4 of them, divided by x squared, because there's 2 of them, and that would be a single power. Now that took us quite a bit of time. It required a lot of space. Wouldn't it be nice if there was a shorter way? And there is. That's where these properties come from. They're essentially shortcuts. So let's take the same example, x to the 3rd times y to the 6th divided by x to the 5th times y squared. And this time we're going to use our shortcut. Now, what is the pattern that you notice? How do you get 4 out of a 6 and a 2? How do you get 2 out of a 3 and a 5? Well, I know 6 minus 2 is 4, and 5 minus 3 is 2. And really what you're doing when you have those big ones is you're taking away factors. And take away is another way of just saying subtraction. So the shortcut here, the shorter way, the property states if you have powers with the same base in a numerator and denominator, you can subtract the exponents. Now, the way I like to do this is not the way that everybody teaches it, but I always like to look ahead and go, where are there more factors? So if I were to take a look at just the x's first, I notice that I have 3 in the numerator and 5 in the denominator. So where are there more? There are more in the denominator. And you can see that over here. I had 5 compared to 3. That means in my final answer, my power with base x will be in the denominator because that's where the remaining x's are going to end up. So when I subtract, I always do greater minus lesser, and you leave it where the greater number is. I'm going to end up with 2 extra x's in the denominator. I already know that because I know I'm starting with more in the denominator. Let's look at the same thing with the y's. I have 6 y's in the numerator and I have 2 in the denominator. Which one has more? Well, last time I checked, 6 is more than 2, and we see that over here. There are way more y's in the numerator than the denominator. So I know in my final single power, I'm going to end up with y's in the numerator, and I'm doing greater minus lesser 6 minus 2. All right, here we go. Well, if I take the 2 y's away from the 6 y's, that leaves me with 4 y's in the numerator. And if I take the 3 x's away from the 5 x's, that leaves me with 2 x's in the denominator. And I'm done with a fraction of the time and way less work. So quotient of powers, as long as they have the same base, you can cancel out those big ones. You can subtract the exponents, but keep in mind where the greater number is. It will oftentimes change. All right, 2 down, 3 to go. Yes, 2 plus 3 is 5. 2 down, 3 to go. The next one's going to be power of powers. Okay, power of powers. So again, the property is telling you what we're looking at. Now we're going to be looking at a power. So not a product, not a quotient, but a power. But the base of this power is another power. It's like a power within a power. It's totally crazy. I know. Okay, let's look at an example here. We'll keep this pretty basic, and then we'll get a little bit more complex. So this one shouldn't take too long. Let's say I have m to the 4th raised to the 3rd power. Like I said, pretty basic. Okay, well, let's look at what this actually means. This means that I'm multiplying whatever's inside the parentheses by itself 3 times. That's what powers mean. Like whatever it is, it could be x's, it could be y's, it could be numbers, it could be happy faces. Whatever it is, you're multiplying it by itself 3 times. That's what that exponent is telling me. So the long way would be to write it out. So whatever is inside the parentheses, I'm multiplying that, m to the 4th, by itself 3 times. That's what that actually means, which means I have 4 m's here, 1, 2, 3, 4, times 4 more m's there, times 4 more m's there. Essentially 3 groups of 4 m's. Now, groups of is a terminology that we use when we're referring to multiplication. 3 groups of 4 is the same thing as saying 3 times 4. Keep that in mind. Because if I have 4 here, and 4 there, all together, that makes 16, excuse me, not 16, 12 total m's, right? Adding up 4 3 times is equivalent to just multiplying. That's why in the shortcut, if you have a power raised to an additional power, a power of another power, the shortcut says you're just taking 3 groups of the base. That means I'm going to take m to the 4th and add it up 3 times. 4 m's, 4 more m's, 4 more m's, for a grand total of 12 m's. I know, it's crazy how much faster the shortcut is using the actual patterns and the properties. Okay, so at this point, we've gone over the 3 that we've seen before. That leaves 2 new ones. The first new one, we've actually kind of gone over when we did coefficients. It's called a power of a product. Power of a product. Again, it's telling us what we're looking at. We're going to look at a power whose base is a product. So very similar to power of powers. This time, though, the base is a product. Let me show you. So in this case, let's say I had something like 2x squared y to the power of 4, something like that, right? Now, this is, the entire expression is a power because it has a base raised to an exponent. But if you look inside the parentheses, this is not a single power, this is a product. This is 2 times x squared times y. That's why we call this a power of a product, because it's a product inside the parentheses. All right, so the long way here is exactly the same as what we would do in power of powers, just like the last example. This exponent is telling us that we're going to multiply whatever's inside the parentheses by itself 4 times. That means I'm doing 2x squared y times 2x squared y times 2, whoops, forgot my parentheses there, 2x squared y times, you got it, 2x squared y. 4 total times. Now we start looking at, well, like, okay, what can I actually do here? What do you notice? Well, I notice 2 is being multiplied by itself 4 times. So basically 2 gets multiplied 4 times. X squared is also multiplied 4 times. So I also have x squared multiplied 4 times, and y is multiplied 4 times. So that's y multiplied 4 times. And now I can go here and I can simplify. 2 to the power of 4, well, 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. So that's just 16. And in this case, because this is technically a coefficient, I do actually want to do that math. X squared to the power of 4. Wait a minute, that's a power of a power. What did we just learn? What can we do with these exponents here? Think about it as that means 4 groups of 2 x's. In other words, we can multiply them. 2 times 4, that means there's a grand total of 8 x's there. So x to the 8th, and then this is just y to the 4th. 4 y's means y to the 4th. And there you have it. That's the long way. So again, inside the parentheses of a power, that just means that's what you're multiplying by itself. Now there is actually a shorter way to do this. The short way, 2x squared y to the power of 4, looks like this. Anytime you're dealing with a product, my first recommendation is put some space in there. Separate those factors. Put in multiplication symbols so that you remember that each of these stand on their own. That 2 is not connected to that x squared. It is by multiplication, but it's not affected by that power. So my first recommendation, always put some space in there. So even in the short way, the first thing I would do is I'd space these out a little bit. Make sure that you see the 3 separate factors of this product. Now, as we saw over here, what ended up happening is that I multiplied 2 by itself 4 times, x squared by itself 4 times, and y by itself 4 times. So we can actually skip that long step of extending it because we know what's going to happen. 2 will be multiplied by itself 4 times. Then x squared will be multiplied by itself 4 times. And then y will be multiplied by itself 4 times. Some teachers have said this is similar to how the distributive property works, and that everybody gets the exponent. All the factors get the exponent. Basically, I just look at it as 2 is multiplied 4 times, x squared 4 times, and y 4 times. And then we do the math like we did down here. 2 to the 4th power is 16. X squared to the 4th power, that's 4 groups of 2 x's, is x to the 8th. And y to the 4th power is just y to the 4th power. It's the exact same thinking that's happening over here, but with way less work and way less writing. That's called a power of a product. That is our 4th property. We have one final property, and you could probably guess what it is. We've done product of powers, quotient of powers, power of power, power of product. What could possibly be the last one? Did you say power of a quotient? Because if you did, you would be correct. Yes, our last final property is called the power of a quotient. So again, the name tells you what you're looking at. We're looking at a power, but this time inside the parentheses is a quotient. Let's look at an example. Let's say I have something like 2x squared divided by 3y to the 4th, all raised to the power of 3. Yeah, I like that. Okay, the long way, you know by now, the long way means you're going to have to expand it. You're going to have to write it all out, which means I'm probably going to run out of room, but we'll do it anyways. Okay, this Exponent means whatever's inside the parentheses, the entire thing gets multiplied by itself 3 times. That means, excuse me, I'm going to have 3 quotients, 2x squared divided by 3y to the 4th times 2x squared divided by 3y to the 4th times 2x squared divided by 3y to the 4th. Oh, so much writing, right? So I expand it and then I try to condense it. Like I look at like, what do you actually see? I see, starting at the top, I see 2 being multiplied by itself 3 times in the numerator. So I know in my numerator, 2 gets raised to the power of 3. I'm going to multiply 2 times 2 times 2. I'm also going to multiply x squared by itself 3 times. So that means x squared also gets raised to the power of 3. That's all happening just in the numerator, though. What's happening in the denominator? Well, 3 is multiplied by itself 3 times, which means 3 will be raised to the power of 3. That's what repeated multiplication is. It's just a power. And then y to the 4th gets multiplied by itself 3 times. We have y to the 4th raised to the power of 3 as well. Let's go in and simplify. 2 to the power of 3. 2 times 2 is 4. 4 times 2 is 8. X squared to the power of 3, there's another power of a power. If I have 3 groups of x squared, 2 here, 2 here, and 2 there, that means a grand total of x to the 6th. 2 times 3 is 6. 1, 2, 3, 4, 5, 6. A bunch of different ways to look at that. That's in the numerator. In the denominator, 3 to the power of 3. Well, 3 times 3 is 9. 9 times 3 is 27. And then y to the 4th to the power of 3, that means 3 groups of 4 y's, or 4 here, 4 there, and 4 there. 4 times 3 is 12. Oh, that was so much work, right? Like, oh, like it takes forever. My hand hurts. You love to come up with excuses. Well, that's why we have shortcuts. Shortcuts are the excuse eliminators. All right, let's see if we can shorten this up and do way less work. So we have 2x squared in the numerator, 3y to the 4th in the denominator, all raised to the power of 3. Let's think about what we looked at our last one. The first thing I noticed is that we got some coefficients in there, we got some products in there. I always say, make some space. Give them some space. Blah, 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 blah. Give them some space, okay? So the first thing I'm going to do is I'm going to separate this 2 from the x squared in the numerator and the 3 from the y to the 4th in the denominator, because I want to make sure that I see these as individual factors. Now, what actually happened? If you look down here, all individual factors were all raised to the power of 3. 2 got multiplied 3 times, x squared was multiplied 3 times, 3 was multiplied 3 times, y to the 4th was multiplied 3 times. Well, that just means that all of these factors, all 4 of these, are going to get raised to the power of 3. So we don't even have to write it out. We already know that's going to happen. So essentially, we could just write it like this. Oops, I don't even need that big parentheses. I don't even know I did that. Let's set up a fraction bar. In the numerator, 2 will be raised to the power of 3, because 2 times 2 times 2, that's what that means. X squared will be raised to the power of 3, because x squared times x squared times x squared, that's what that means. In the denominator, 3 will be raised to the power of 3. That's what that means. And y to the 4th will be raised to the power of 3. Does this look familiar? Yeah. And it's very similar to the power of a product. Everything gets the exponent because everything's going to be multiplied by itself 3 times. Let's go do the math. 2 to the power of 3. 2 times 2 is 4. Times 2 is 8. X squared to the power of 3. That's x to the 6th. 3 to the power of 3. 3 times 3 is 9. Times 3 is 27. And y to the 4th to the power of 3 is y to the 12th. And guess what? We are done. My hand feels great. It isn't cramping up or anything because I barely wrote down a thing. Those are your 5 properties. Now notice in all of these examples, we did not include negatives. So we're going to wrap up this video by looking at a few examples. I'm thinking we'll do 3. 3 kind of tougher examples that mesh together different properties and that include negatives, just for funsies, because why not? So get your new piece of paper ready, and here we go. All right, we've got a super fun exit ticket planned for you. Super fun usually means that it looks a lot tougher than it actually is. Let's get this right up there and close. Okay, so go ahead and write this one down if you're following along. Number one, 4x squared times y to the negative 3, all raised to the power of 5. Number two, 4y cubed divided by 2y to the negative 4. And then number two. Number three, 3x to the fifth, y to the negative third divided by 6, x to the negative second, y to the fifth, all raised to the power of 2. Oh my gosh, so much fun. I love this stuff. All right, let's take this one step at a time. Let's look at like, what can we actually do? Oh, I just realized I made number one a little bit tougher than I intended. That's okay, we'll do it anyways. Okay, here we go. What I noticed on number one is that this is a power, and the power has a base that's a product. So that would make this a power of a product. That's how you would classify number one, power of a product. So what do we always do when you see those coefficients in there? Give them some space, right? Step one, separate them out a little bit. So I'm going to separate the 4 from the x squared and the y to the negative third. In fact, I'm going to take out this little squiggly line because it's cramping my space that I'm trying to give them, all raised to the fifth. Okay? So give them some space. Now I know what's going to happen next. If I were to do this the long way, I would end up multiplying 4 by itself 5 times, x squared by itself 5 times, y to the negative third by itself 5 times. But I don't have to do this the long way because I already know that. So the next step is just raise each one to its own power. 4 gets raised to the power of 5, x squared gets raised to the power of 5, and y to the negative 3 gets raised to the power of 5. Let's go in and simplify. 4 to the power of 5. 4 times 4 is 16. 16 times 4 is 64. Times 4 is 256 times, I'm out. I don't even know. You know what? We're just going to leave it as 4 to the power of 5. By the way, if you can't simplify it mentally, just leave it as a power. Like, it's totally fine, at least for me. X squared to the power of 5, that's a power of a power, which means we can multiply those exponents. 2 times 5 is 10. And y to the negative 3 to the power of 5 is y to the negative 15. Everything is great, and we are done, right? Wrong. What's wrong here? Y is unhappy. Why is y unhappy? Because it has a negative exponent. We don't like negative exponents. Now, notice y is the only part that's unhappy here. 4 gets a positive exponent of 5. X has a positive exponent of 10. Y is unhappy. How do we make y happy? How do we make negative 15? That negative exponent a positive? Reciprocal, that was my reciprocal hand. Reciprocal of the base. Take it out of the numerator, put it in the denominator. So our final answer here, where can I write this? Would be 4 to the 5th and x to the 10th are still in the numerator. They're happy. Y to the 15th gets moved to the denominator. And there you go. Numero uno is complete. Let's take a look at number 2. All right, this one's actually a little bit simpler, but these are ones that I know a lot of students struggle with. So I figured, yeah, let's go over it. Okay, number 2 is a quotient of powers. How can I tell? Because it is a quotient, excuse me, and there are powers in the numerator and denominator, which means we're going to use those properties. Now, first thing that stands out to me is that they're too close. I've got coefficients, we need some space. Let's put some space in there. I always say make space. They're cramped, give them some space. It will allow you to see them a little clearer. All right, cool. Now we can actually go in here and treat these separately. The first thing I see is 4 divided by 2. Well, hopefully you know 4 divided by 2 is 2, and that 2 would be in the numerator. In other words, we're simplifying this to a 1 and a 2, so a 1 in the denominator, 2 in the numerator. So that already tells me that I'm going to have 2 in the numerator, 1 in the denominator. I'm thinking ahead. Now, in a quotient of powers, you have to remember where is the greater number of whatever the base is. So where's the greater number of y's? We got 3 in the numerator, negative 4 in the denominator. 3 is greater, which means we're going to end up with y's in the numerator. So remember, it's always greater minus lesser. So in the numerator, we have y, which is a 3 minus negative 4. There are negative 4 here. In other words, these 4, because they're negative, they're unhappy, will get moved into the numerator and added on to those 3, because subtracting a negative is equivalent to adding a positive. And that brings our final answer to 2y to the 7th. A couple things I did there. One, I added the 3 and the 4. Why did I add? Because subtracting a negative is equivalent to adding a positive. And I got rid of the 1 in the denominator because we don't need it. Final answer, 2y to the 7th. See, easy peasy. All right, number 3. So much fun, number 3. I actually really like number 3. I like number 3 because it's way simpler than it looks, okay? There's a couple ways to do number 3. Here's how I would suggest doing it. I don't like the fact, first of all, this is a power of a quotient. And inside that quotient, you also have products. So it's like a power of a quotient of a product. We're like starting to mesh together these properties. But anyways, what I don't like about this is that I don't really like doing math inside of parentheses. I would almost like to get rid of the parentheses like I did here. Notice how I left the negative to the very end. I like to get rid of the parentheses and then I like to do the rest of the math. So the first thing I'm going to do is I'm going to try to get rid of this exponent too. But before I can do that, you got to make space. Now here's another way to make space because I'm literally running out of space, is that you can just put in multiplication symbols to separate them. So if you don't have enough space on your paper to physically rewrite it again, you can just put in multiplication symbols just so that you see those as separate entities. Now everything gets raised to the second power. 3x to the 5th, y to the negative 3rd, all gets raised to the second power. In the numerator, in the denominator, 6x to the negative 2 and y to the 5th all gets raised to the second power. Here we go. All right, in the numerator, we have 3 raised to the second power times x to the 5th raised to the second power times y to the negative 3rd to the second power. In the denominator, 6 to the second power times x to the negative 2 to the second power times y to the 5th to the second power. That might look like, why would you do that? Well, here's what's nice about this. Now I can just simplify each of these individually. The parentheses will be gone. Then I can deal with the rest of it. All right, 3 to the second power is 9. Bring this one down here. 9. X to the 5th to the second power, that's 2 groups of 5 x's. That's x to the 10th. Y to the negative 3rd to the second power is y to the negative 6th. In the denominator, 6 to the second power is 36. X to the negative 2 to the second, negative 2 times 2 is negative 4. And y to the 5th to the second is y to the 10th. Whew, wasn't that fun? Now, what's nice about what we did here is now this looks more similar to number 2 because we got rid of the parentheses. All right, here we go. We have probably like 2 more steps to go. They still look pretty crunched together, so I'm going to use a different color here, make space again. If I had more room on this whiteboard, I would probably rewrite it. Now I can go in there and look at them each as separate entities. So let's start with the 9 and the 36. Can 9 and 36 be simplified? Does 9 go into 36? Yeah, 9, 18, 27. Yeah, it goes into it 4 times. So I can simplify this. We would be left with a 1 in the numerator and a 4 in the denominator. So that leaves us with, let's write out what we got. We got a 1 in the numerator and the 4 in the denominator. Okay, moving on. Let's look at the x's now. We have 10 in the numerator, negative 4 in the denominator, which has a greater number. 10 is greater than negative 4, which means we're going to end up with x's in the numerator. These negative 4, to make them positive, they have to be moved into the numerator, meaning they'll be added on. So in the numerator, if we were to do the quotient of powers, which means subtract, greater minus lesser, we have 10 minus negative 4. Let's look at the y's. We've got 10 in the denominator, negative 6 in the numerator. Pretty sure 10 is more, which means we're going to have y's in the denominator. These 6 will move down, and we have 10 minus negative 6, because you're always subtracting whatever the exponent is. All right, here we go. This will be our last step. Ready? 10 minus negative 4 is the same thing as 10 plus 4. So that leaves us with 1x to the 14th, because those 4 moved into the numerator, added on. And the denominator, 4, and then we have 10 minus negative 6, which is equivalent to 10 y to the 16th, because those 6 moved into the denominator. And we are done. Crazy. But if you think about the sheer amount of work that I just did, I did it in what, 4 steps, 1, 2, 3, done. Can you imagine writing all of that out and then going in there and trying to simplify it? I couldn't. Now, some of you might think, well, what about this 1? Do I leave it there? Do I not leave it there? You could leave it there, or you could take it away because it's just the hidden 1. It's totally up to you. Do you want to leave it there because it shows you what you did with the fraction? You can. In your Algebra 2 classes down the road, they probably will want you to eliminate it because it's not necessary. All right, that is it for this video. We looked at 5 exponent properties, and we did 3 kind of trickier examples. And yeah, that's just about it. So I hope that that made sense. And if it didn't, we'll go ahead, we'll just keep working on it and keep clarifying. So that is it for today. Have lots of fun using your properties of exponents, and I'll see you next time.